on what the fundamental counting principle is. The fundamental counting principle states that, and I'm going to kind of write this in like a layman's terms type thing, not like textbook definition, but essentially, the fundamental counting principle says that if there are p ways to do one thing, and q ways to do another thing, then there are p times q ways to do both things. And I'm being kind of vague here with like do one thing, do another thing, because the context of the problem is not really significant. It's just if there are a certain number of ways to accomplish a task, and then is a certain number of ways to accomplish a totally different task, then the number of ways there are to accomplish both tasks is just the product of the two numbers multiplied together. And that's essentially what the fundamental counting principle is. It allows us to solve a bunch of counting problems, such as this first example here. And I'll do this example with you to kind of show you why this products property works for the fundamental counting principle. Essentially, it comes down to if you were to list every single possible outcome for the two events, you'll end up with this product. So, question says you buy 2 pairs of jeans, 3 shirts, and 2 pairs of shoes. An outfit consists of 1 new pair of jeans, 1 new shirt, and 1 new pair of shoes. Use the fundamental counting principle of counting to determine how many different outfit combinations are possible. So what we do in this situation is we split our main task, which is an outfit, into its 3 components. So to make an outfit, we have to have jeans, a shirt, and shoes. Right? And in order to, we're splitting this outfit task into 3 different tasks, and we're going to write down the number of ways each task can be completed. So the number of ways that a pair of jeans can be chosen is 2, because there were 2 jeans, 2 pairs of new jeans that you bought. So there are 2 ways to complete the jeans task. The shirt task, there are 3 new shirts, therefore there are 3 different ways to choose a shirt. And finally, for shoes, there are 2 new pairs of shoes, so there's 2 ways to choose a pair of shoes. And multiplying all of these together, we see that there are 2 times 3 is 6, 6 times 2 is 12. There are 12 different outfits. And then part B asks us to construct a tree diagram. And here we're going to work with these 3 tasks, and we're going to create a tree diagram where each branch of the tree is going to represent a different outfit. So we're going to start the problem by representing the choices for the jeans. Since there are 2 choices for pairs of jeans, we're going to split into 2 branches here to begin with. right? And each of these branches is going to be a different pair of genes. So we'll call this genes 1 and genes 2. Since we don't actually have like the names of the genes or the brands or anything, we'll just call it genes 1 and genes 2. From there, whether we chose genes 1 or genes 2 for the outfit, in either case, we're going to need to choose one of 3 shirts. So from here, when we're at this point, or this point, we're still going to split into 3 branches. So we'll have one of the branches continue forward. One branch will go up, one branch will go down. So, and then we're going to do the same thing for the genes 2 pathway. In either of these cases, we have 3 options. We have shirt 1, shirt 2, and shirt 3 to choose from. There are 3 different shirts. And if we chose genes 2, we still have the same 3 options. Shirt 1, shirt 2, and shirt 3. Once we've chosen, let's say, gene 1 and shirt 1, we still need to choose a pair of shoes to go with that outfit. So then from this point, we will need 2 different branches because we need to choose one of 2 shoes. But we need to do that for any possible combination. So for example, if I go to jeans 2 and shirt 1, this also has 2 different options for the shoes. So each of these is going to split into 2 branches. Because there are 2 choices for the shoes. You can say shoe 1, shoe 2 for all of them. I guess we can write this on the end of the branch since we're not splitting anymore after this point. So shoe 1, shoe 2. And the total number of outfits is represented by the total number of end branches we have here. Because each one of these ends comes from a choice of jean, a choice of shirt, and then a choice of shoe. Right? Each one of these end branches is not just a shoe, it's a shirt, a jean, and a shoe choice. So there are 12 different outfits that we're seeing by counting the number of end branches. Any questions on that? On what the fundamental counting principle is? Okay. I do want to go over, I don't want to do all of these, but I do want to go over the factorial symbol here. Let me add a new page here. The bottom example is here where we have the factorial symbol with the exclamation point. if we were just given the tree diagram and we had to find the total outcome, would we count the last bracket or others? If you're given a tree diagram and you want to count the total number of outfits, you count how many total ends you have. Yes, how many of these there are. That would, each one of these is a different outfit. I know I keep saying shoe 1, shoe 2 over and over again, but if you chose any one of these, that comes from all of the choices that were made to get to that choice. So the number of things at the end are the last bracket. This is the 12 that we're counting for the outfits. Okay, let's talk about what a factorial is. We have this exclamation point symbol that is maybe new for you guys. So what that is whenever we have a number with an exclamation point, we read that as n factorial, which is essentially a falling product. What do we mean by falling product? Sorry, falling product starting with n and ending at 1. Meaning we do n times n minus 1 times n minus 2 and so on. We multiply all the way down to 1. I guess I should say down to 3 times 2 times 1. No matter what n is. If n is 7, then you do 7 times 6 times 5 times 4 times 3 times 2 times 1. So you multiply all the way down. For example, this 6 factorial here is 6 times 5 times 4 times 3 times 2 times 1. And the answer for that is 720. If it's a larger number like 83, you cannot calculate that, neither by hand nor by calculator, but we can do things where we simplify factorials, which I'm going to talk about right now, where you may see large factorials like 83 factorial, but they're going to simplify because they're part of a fraction. So when we have a fraction such as this one here, in part C, excuse me, we know that 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. It goes all the way down. But what we do as a kind of a shortcut is we know that this 5 factorial in the denominator is also 5 times 4 times 3 times 2 times 1, right? Which exists within this 8 factorial, right? If I were to write the 8 factorial out, that's 8, 7, 6, 5, 4, 3, 2, 1, right? And then this denominator, 5 factorial, is 5 times 4 times 3 times 2 times 1. So within this 8 factorial lives a 5 factorial, which is just this part of it. Right? So what we do instead of writing it all out is, what we do is we say 8 times 7 times 6 times 5, but instead of writing 5 times 4 times 3 times 2 times 1, I'm going to leave this as a 5 factorial here, which stands for 5 times 4 times 3 times 2 times 1. And now we have the same thing, the 5 factorial in the numerator and denominator, which we can just cancel. Both of those are going to be the same calculation, so we can cancel those. And then we know that 3 factorial is 3 times 2 times 1, so we'll write this as 8 times 7 times 6 over 3 times 2 times 1. And then we can continue to simplify this. I know that 3 times 2 is 6 in the bottom, which means I can take that 3 times 2 and simplify it with the 6 on top. And those are gone. So now we end up with 8 times 7 divided by 1, but there's no need to write the divided by 1, which gives us a 56. All right, so there are ways of simplifying factorials without actually computing the big numbers. So we never had to calculate what 8 factorial was. And as soon as you get to like 12 factorial, 13 factorial, those numbers are going to get really, really large, and you don't really want to calculate them. Okay? So if you're ever in a situation where, like somebody asked about what if it was like 83 factorial? No, a question will not ask you to compute 83 factorial, but it may ask you to do things like calculate 83 factorial over like 4 factorial, 79 factorial. We may have something like that pop up somewhere, right? Which is similar to what we saw here. The reason why we're seeing this stuff is because when we get into more and more different methods of counting problems, we're going to see these functions show up. So how would we do this one? Well, we would do the same thing we did with this 8 factorial, 5 factorial situation. When I start writing the 83 factorial, I have 83 times 82 times 81 times 80 times 79. And as soon as I see 79, I know that the rest of this product, all the way down to times 3 times 2 times 1, is the same thing as the 79 factorial down here. So as soon as I see that 79, I'm going to stop and write factorial. And in the denominator, we have a 4 times 3 times 2 times 1. But then we also have a 79 factorial. I'm going to leave that 79 factorial as is because I know that I can cancel those 79 factorials. And now what we get to do is just calculate what this is, which our calculators can do. Or we can simplify some things by hand. I know that 4 times 2 is 8, for example. And then if I get rid of the 4 and the 2, I can turn this into a 10 because I'm dividing both the top and the bottom by 8. And then I'm sure 3 goes into one of these. 3 goes into 81 27 times, I think. So we can simplify that to 27. So then our result at the end will be 83 times 82 times 27 times 10. Again, not something I would do by hand, but a calculator can give you the answer to that product, right? If you try to punch in 83 factorial into your calculator, which your calculator should have a factorial button, there should be an exclamation point somewhere on your calculators. Let me see what a scientific calculator looks like, because I know there is a... on a scientific calculator, you click on, I believe you click on the PRB button. I guess we'll make a note for it here. For calculator, use PRB to find, if you haven't already found it, to find the exclamation point. Does anyone have a scientific calculator on hand? And if you do, can you press the PRB button? And then
the PRB button.
It is the PRB button?
Yeah.
There's an exclamation point in there on the list?
Yeah.
Okay, good. So then on the calculator, if you wanted to compute like 6 factorial, you would press 6 first, and then you would press PRB, and then you would find the exclamation point from there, and then it would add it next to the 6 on your main screen. All right, so there's a way to do factorials on a calculator, except what I was just saying is that it won't do 83 factorial, because 83 factorial is like much too large of a number for your calculator to do. So in the case of something like this, you may be able to put all of this into the calculator, but it may give you an error. So you may have to simplify down to this first, and then just calculate this product using your calculator, okay, without using the factorial number at all. Okay, so I guess we should finish this one. Did anyone calculate this product? 83 times 82 times 27 times 10 gives us 1,837,620. So that's what 83 factorial over 4 factorial 79 factorial is. I have a question here. Since the 3 factorial and 5 factorial are next to each other, do they multiply? Yes. So when we write numbers next to each other like this, this is essentially multiplication. I know we're getting to a point where we're almost leaving off the dot even for multiplication. I think it's happening in this situation because the factorial symbol is there. So if you see 3 factorial, 5 factorial next to each other, that's multiplication, yes. And when I write 4 factorial, 79 factorial, that's multiplication, yes. Good question. Any other questions on